All right, so now let's talk about absolute maximums and minimums. And I'm going to be very transparent. This is a very sucky process. It is very tedious, it's very long, and it is not fun. So just bear with me. We're going to do one example. And then the other one, we might do it in a separate video or in another class. But it's a very long and tedious process. So let's go ahead and just start. So back in Calc 1, what you usually must have encountered is maybe you have some sort of function like x cubed minus 2x plus 1. And they wanted to know what the maximums and minimums were, the absolute maximums and minimums were, like maybe in the interval from 1 to 5. So there's a couple things that you did here. So one of them is that you set the derivative equal to 0 and you solved, right? And you got some x values, okay? So you got some x values. If the x value was outside of this range, you would get rid of it. So for example, if you got x equals 7 as one of the answers and x equals 2 as one of the answers, you would get rid of 7 because 7 is not within that interval. So you would use x equals 2. And the second thing what you would do is you would test, okay? You would test and plug back into f of x. And whichever one was the bigger one, right, the biggest one would be your absolute max. And whichever one was the smallest one would be your absolute min. That's how we kind of did it. And we were saying that because, and the way that we did it was that not only did we plug in x equals 2, we also plugged in 1 and 5. Because if we kind of take a look at the graph, and let's say you had x equals 2 here and then 1 to 5, well, it can have a critical point there, but you can see here that maybe this was the maximum, but you can see that at 1, you have a minimum. It's the lowest y value. So that's why you needed to check the endpoints, because you're only looking at this piece of the graph, not the whole thing. So if you're looking within this piece, you can find some critical points at the endpoints. So that's why you had to kind of check that. So the same thing is kind of happening with multivariable functions. So with multivariable functions, you can have maximums and minimums within the boundary. So in this case, you have a boundary in the x direction and in the y direction. Okay, so now you have a double boundary, and you can have some maximums and minimums in the inside as well. Now the challenge here is that sometimes they can appear in the corners, sometimes they might be along the boundary, sometimes they might be within. So what you gotta do, and this is where the tedious part comes in, what you have to do is not only do you have to check the boundaries of all of these guys to check if they're in there, but you also got to check the corner points to see if there's a potential maximum or minimum in there. And you also got to check everything that's inside. So that's what what makes it a little tedious, because now that we have this x and y dimension, we kind of have to check everything within the boundary, everything inside of it, every single corner. There's a lot of things that we got to do. So again, here's the extreme value theorem. If f is continuous on a closed interval from a to b, then f has an absolute minimum or maximum, because it can also be the endpoints that are the maximums or minimums. All right. So the extreme value theorem for two variables is the following. So if f is continuous on a closed bounded set D in R2, then f attains an absolute max and absolute min, okay, in this set D. Okay, so here are closed sets. So closed sets means that you have boundaries, so everything is included all around. So you can have circles, you can have rectangles, you can even have triangles in there, right? And you have all these values inside. So these are closed sets. So as long as the function f is closed and it's also bounded, then an absolute maximum will always exist. Now, things that are not closed, for example, that's not necessarily true, because now you're not really including what's on the outside. So we can't quite be, we quite cannot know that. So again, we're going to assume that a lot of them are closed. How do you know they're closed or not closed? They usually tell you. So for example, if you're looking at a circle that's not closed, this is a circle that's closed. This is a circle that's not closed. Oops, that's totally not right. So let's just write one. And let's make this a less than. This circle here is closed. circle of radius 1, and notice that it's equal to 1, so you have that boundary. This one's not closed. It's not including the boundary, okay? So that's the issue here. All right, so how do you find them? All right, so the way that you find these extreme values, you want to find the critical points in D, so just like how we did it before. And then you want to find the extremes on the boundary, okay, which includes the corners. The largest f is the absolute max, and the largest f is the absolute minimum, right? Again, this is a long and tedious process. So we're not using the second derivative test. That was to classify local mins, mans, and saddle points. Here everything is enclosed within some region. So imagine that I'm enclosing this thing. I'm not looking at the whole thing. Within this region, which one's the maximum and which one's the minimum? That's all I really care about. All right, so let's just start off with an example. And this example is probably going to take out the whole video. All right, so let's go ahead and just do this example. So we want to find the absolute minimums and maximums for this function. And this is over the rectangular region given by x is between -1 and 1, and y is between -1 and 1 as well. All right, so the first thing that we want to be able to do is let's take the partial derivatives. So I'm going to take the partial derivative with respect to x first. So this is going to give me 2x minus 4xy. And we're going to set that guy equal to 0. And then we're going to take the partial derivative with respect to y, which will give me 8y minus 2x squared. And I'm going to set this guy equal to 0. All right, so let's see what we can do here. Let me solve for this f sub y. Sometimes one of them is easier than the other. It really just doesn't really matter which one you use. But I'm going to go ahead and set this guy equal to 0. I'm going to solve for this one. So you're going to have 8y equals 2x squared. So y equals 1/4 x squared. Ooh, maybe the other one would have been better. It doesn't matter. So I'm going to go ahead and plug this guy over here. So you're going to have 2x minus 4x x squared over 4 equals 0. So I just plugged in the 1/4 x in here. And what you're going to get is 2x. Oh, nice. The 4's go away. And you get minus x cubed. So I'm going to factor out an x. So you're going to get 2 minus x squared equals 0. So you're going to get x equals 0, and 2 equals x squared, so x equals plus or minus square root of 2. All right, now before we continue, okay, so we got a couple points. I got a couple x's. Let's take a look at the rectangular region, all right, because this is where we don't want to do more work than what we need to. So let's look at this region, this rectangular region that they gave us. So we got x is between -1 and 1, and we got that y is between -1 and 1. So this rectangular region looks like this, and notice that everything is included in here. All right, so we got all of these guys, all right? So if you take a look at square root of 2 over square root of 2, that's like 1.4 something, right? So in other words, this point, this x equals plus or minus square root of 2, is not in this boundary. We are only looking for values that are inside of this region. And unfortunately, square root of 2 over 2 does not cut it. So these guys, we're going to exclude them because they lie outside of our boundary. So the only one that really is worth it is x equals 0. Okay? But then again, if the y value is like 7, then we can exclude that one as well. But we're already going to exclude x equals plus or minus square root of 2 because we already went way past the boundary of x. Okay, x, remember, can only be between -1 and 1. X in this case was square root of 2, positive and negative, so we're going to exclude both of them. So we're only going to look at x equals 0. So y equals 1/4, 0 squared, so we just get 0. So the point 0, 0 is a candidate. It lies right there. It's inside of the region. This one is good. All right. Cool. All right. So now what we're going to look at, and this is where it sucks, we're going to look at the boundary now. So what we did is we looked at the inside. So this was kind of like the first step. This is the inside of the region. And now what we're going to look at the boundary. And notice that in the boundary, you have 4 things to test. So basically you have this guy. We're going to call that L1. So this is the first boundary, L1. We got this guy. This guy's going to be L2. We got this guy. This guy's going to be L3. Okay, and this guy, we're going to call it this L4. So we got all these different ones. All right, not only that, but remember, they can also have it at the corners. Okay, so you can also have some corner points. Okay, so you can also get answers in the corners. So at 1, 1, 1, negative 1, negative 1, negative 1, and negative 1, comma 1. So these can be potential candidates. So let's go ahead and make a little table. I like making a little table to kind of keep track of all my points. So let's write some critical points right here. And then later on, we'll classify them as extrema. Is it an extreme or not? So right now we got the points 0, 0. So 0, 0 was one of my critical points. I'm going to put in all my corners as well. So I'm going to put in 1, 1, 1, negative 1, negative 1, 1, and negative 1, negative 1. So this one was just the critical point that we just found out, this 0, 0. These guys are just a corner point. So these guys were my corners. So now what we got to look at each individual boundary. All right, here we go. Let's look at L1 first. So we're going to take a look at what exactly is happening in this region from here to here. All right, so this L1 is x equals 1. So we're going to look at L1, and at L1 is when x equals 1. And my y values are somewhere between negative 1 and 1. All right, so we're within this interval. So what I'm going to do, I'm going to grab this function. So this function, what I'm going to do is I'm going to plug in x equals 1 and see, do we have any extreme values in this particular point? So what I'm going to do, I'm going to plug in 1 into the x. So 1 squared plus 4y squared minus 2 times 1 squared y plus 4. All right, and this is going to give me what? It's going to give me 5 plus 4y squared minus 2y. All right. So now what we're going to do, let's call this a different variable, g of y. Let's just call that. We got 4y squared minus 2y plus 5. All right, so we want to know, is there any extreme values within this point? And remember, my y's can only be between 1 and negative 1. So how do we find if there's any extreme points? Well, we take the derivative and set it equal to 0. So take the derivative, set it equal to 0. So this is 8y minus 2 equals 0. So we got y equals 1/4. Okay, so we got y equals 1/4, and this happened when x equals 1. So is 1 comma 1/4 a point in this boundary? Let's see. Yes, it is. 1 comma 1/4 is probably around there. So it can this can be a potential critical point. So I'm going to add it to my group. 1 comma 1/4. Plug that in there. Okay, so this one we got it from L1. Cool. All right, so we checked that one. Okay, now remember we put in the corners, so I don't have to put in the corners anymore. Okay, because they're already in there. Okay, now let's check L2. So we checked that guy. Now we're going to look at L2. I forgot what L2 was. L2 was this guy up here. So here my x-axis is between negative 1 and 1, and I'm substituting y equals 1. So in the function, I'm plugging in y equals 1. So I'm going to plug in y equals 1, and x's are between negative 1 and 1. All right. So I'm going to plug it in. So I'm going to have f of x comma 1. What was the function again? Okay, let me zoom in. So that was, I'm plugging it into, so x squared plus 4 times 1 squared minus 2x squared times 1 plus 4. Okay, and this is going to give me x squared minus x squared. It's going to give me a negative x squared and then a plus 8. All right, I'm gonna call this h of x. So I'm gonna take the derivative of this and set it equal to 0. So the derivative will be negative 2x equals 0, so we get x equals 0. So that means the point 0, 1 is a critical point. All right, that's x was equal to 0 when y was equal to 1. Notice that is 0, 1 already in there? Let's see, 0, 1. 0, 1 is right here, 0, 1. Okay, so that one could be a potential candidate. So guess what? We're going to put it in there. So I'm going to put 0, 1 in here. All right, so that was L2. Now let's look at L3. So at L3, what point was that? So at L3, we had this point, this guy. My y values are from negative 1 to 1, and I'm plugging in x equals negative 1. So I'm going to plug in x equals negative 1. So x equals negative 1, and this is happening between, y is between negative 1 and 1. Okay, so I'm going to plug in negative 1 into my x value. Okay, so that's going to give me, oh gosh, okay. So I'm going to have negative 1 squared plus 4y squared minus 2 times negative 1 squared y plus 4. So this will give me negative 2 and then plus 1. Okay, and then plus 4. So this is going to give me 4y squared minus 2y plus 5. I think that's what it is. Okay, so I think that's what we got. Yes. All right, so we're going to take the derivative of this. I'm going to call this, I don't know, k of x. So I'm going to call k prime, k prime of y. So I'm going to take the derivative with respect to y. We're going to get 8y minus 2 equals 0. All right, and you're going to get y equals, equals 1/4. Okay, so at x equals negative 1, I get y equals 1/4. So that's this one over here. Negative 1, 1/4 on there. And notice that that lies within the boundary, so we're going to have to put it in there. So negative 1 and 1/4. Cool. All right, now let's do our very last one, which is going to be L4. So line number 4. And notice that at L4, which is this guy, your y equals negative 1. And your x's are between negative 1 and 1. So y equals negative 1. And your x's are between negative 1 and 1. All right, so let's plug that into our function. Okay, so you're going to get, so I'm going to plug in f of x and then negative 1. So you're going to get x squared plus 4 times negative 1 squared minus 2x squared times negative 1 plus 4. So let's see what you get. You're going to get a 3, I think. A 3x squared. So I'm going to call this, I don't know, a of x. So this is going to be 3x squared plus 8. Take the derivative of this guy. 6x equals 0, so x equals 0. Okay, so we got 0, negative 1. Okay, so 0, -1 is within the boundary. 0, -1 is right here. So that one we also have to put in here. Okay, and then we are done. We added the corners, we added the boundary. So these are all points within the boundary. And now what we got to do is plug all of these points into the function. All right, so we're going to plug in every single point, and whichever gives us the biggest one is going to be the maximum. Whichever gives us the smallest one is going to be my minimum. So what I'm going to do, I'm going to do this offline, and I'll tell you what it is. So we got f of 0, 0. F of 1, 1, f of 1, -1, f of -1, 1, f of -1, -1, f of 1, 1/4, f of 0, 1, f of -1, 1/4, and f of 0, -1. So we're going to plug in all of these points into my function. Okay, so let's see what I get. So after many plugging into the calculator, this is what I ended up getting. So our maximum is going to be whatever the biggest number is in this case. And in this case, the biggest number seems to be 11. So it's going to be 11. This is my absolute maximum. So it occurs at these two critical points, which is, I think, is the corners. And my absolute minimum will be the lowest one, which in this case will be 4. This is my minimum. So this one will be my min, my absolute min. And these two guys will be my absolute max. So yes, this is a very tedious problem. It takes a very, very long time. So, and this is where we'll stop now. So there is another problem that we will do maybe in a separate video. But for right now, I wanted to kind of introduce the absolute maximums and minimums and all of its monstrosity.